All right. Can anticipate this to become 2 videos, but might as well do all the examples. So again, let's review from the last video that there are some steps that I think that if you do these are kind of a way that, to kind of break a complex problem into a bunch of manageable steps, that if you kind of understand what all these steps are doing, you'll feel confident in the direction of the induced current or induced magnetic field, whatever it is that you're trying to calculate. And again, let's just go through them again real quick. I'll do a qualitative example. So if you're going to do magnetic induction, we can think of it in terms of this example. So perhaps I have the example where in the previous video I was moving a magnet either closer to or farther away, this coil. Here I'm just going to keep the magnet in place, but I'm going to flip it over. So I'm just going to flip the direction of the poles. So in that case, the magnetic field will start by going out kind of this way and end by going in that way. So there is a change of flux. Even if maybe the start and the end points have exactly the same magnitude, the direction has changed. And then there's, of course, the transition period in between. So again, what do? There has to be a circuit for charge to ultimately flow. In this case, we have the coil. That coil then defines a particular surface, which I will highlight. We were using red. This surface here, which is the surface that we will use to measure the magnetic flux. With that surface, we have to define our dA element, the directionality of the surface element. And again, what this is doing, and I'm going to draw it this way, you can draw it the other way if you want to as well. But I like this because, at least at first, for this particular problem, the magnetic field is going closer to parallel to the direction of dA, and that's going to then, so we're essentially defining positive flux when the magnetic field is going as it is in the start image. And then negative flux will be associated with what's in the end image. And that was important because, again, when we think about how the fluxes change and we think about increasing and decreasing, we don't want to get confused in thinking that things going to zero is what we're looking for. By increasing, we mean it's getting more and more positive, as we have defined, given the dA element I wrote down. Decreasing would really be on the number line towards the negative, based on how we've drawn dA. So we have the dA element, and now we measure the flux in these 2 instances. So in this case, the initial flux, if I look at this first image, this initial flux is going to be positive. So initial magnetic flux is going to be something greater than 0 because of the directionality of the magnetic field, and that it's pointing closer to parallel to the dA element as it goes through that surface. I guess I used the word start, so I'll say start. Then the end, the magnetic flux, is going to be less than 0, because now the magnetic field lines that go through that particular surface are closer to being anti-parallel compared to my dA element that I drew. So, right, it might be, just to give a number, maybe this was 10 Webers or whatever that unit is, Tesla time meter squared. And this might be something like -5. I don't know. If I'm really not moving the magnet, you would think it should be exact, but a physical bar magnet, the field is not exactly a dipole, but there might be, I meant that, actually, I'm taking a drink right at that moment. Because a physical magnet has imperfections and stuff like that. It is, of course, a dipole. There's no magnetic monopoles. So in this case, what is the change? We're thinking about how the magnetic field has changed with time. In all these qualitative examples, I really haven't factored in the amount of time this is taking, because we're being qualitative. Some of the examples I will bring in that time factor as well. And that just means we're thinking about derivatives instead of deltas. Because again, remember, I guess I should have reminded us of Faraday's law. Move that down. Remember, ultimately what we're doing is we're trying to figure out the induced EMF is negative the time derivative of the magnetic flux through this particular surface. Okay, so back to the example. Final minus initial, this is going to be a decrease. So the flux, this is the delta, we might say decreases or is negative. Decreases, by that I mean, again, on the number line, where this is positive and this is negative. The flux might have started here and ended here. Here's a different color. Maybe that's the end, it's the start. Seems like there's a tendency to go that way, in the negative direction. Okay, so we might say decreases, it's negative, whatever. It's not confusing to you. So in that case then, so since it's decreasing or is negative, we will think of this change in flux like a vector, and we will draw this delta in the direction that is anti-parallel to my dA element. So maybe let me recopy the end loop so I can draw some currents eventually. There's the loop. Again, we have our dA element that's going this way. I'll shade it in. And then what we have calculated here is that the change in flux is pointing in this direction. This is the delta flux. So then that means that, back up that step, that the induced magnetic field is going to want to cancel out this change, because again, it wants the good old days of what the flux was at the beginning. So then B induced points in the opposite direction. So I'll say points opposite this change in flux, or in this case, it will be parallel to dA. So then I'm going to draw this green arrow, this, parallel to dA. Covered up dA. So now, and so that's not confusing too much. Let me move this one out of the way a little bit. So then the induced current, we now have to ask ourselves, what direction around this loop will create a magnetic field such that when I test it with the right-hand rule, I get the magnetic field going through the loop in the direction of dA. And not too hard to calculate that the current should go in this direction. Because then, if I imagine a big loop around that current, it's going to go like that. On the other side, it's going to go like that. If the current is flowing in that, I guess, counterclockwise from this perspective direction. Okay. So there's one idea of kind of flipping a magnet. Let's try one that's a little bit more involved, and then we'll do some quantitative ones. So let me have a new page. Oh look, and I've conveniently already put everything here. I don't read that one next. So you did this in lab, but let's think about what goes on when you drop a magnet through a copper tube. So here we have a little magnet. I think this moves on the screen too. What we're going to do is we're just going to drop it through a copper tube. Now, if I just took a little plastic ball or marble and dropped it through a copper tube, we could calculate how long it would take for it to go through the tube, and it really wouldn't be that impressive an experiment because it would just kind of fall due to gravity. It's a little marble, it's probably not a lot of drag forces or anything like that, and it would fall kind of what we would expect. But then, as you saw in lab, when you drop the magnet through the copper tube, it took much longer for the thing to get to the bottom. Something was retarding the force, or retarding the velocity. It had reached some terminal velocity as it fell through. What forces are at play, and can we understand why, at least qualitatively? I did see some YouTube videos that did like a dipole approximation and actually did the math, which was kind of fun. So if you feel like some polar coordinate integrals, you can look those up. So let's see. So what we're going to do is, in the setup, is we're going to drop a magnet through a copper pipe. And do a force analysis. And then we're going to want to ask, why then, when I take an aluminum pipe and drop the magnet through, that it does not, it still takes longer than if there was no tube, no pipe at all, but it gets out of the pipe faster than it did with copper. So copper seems to be stopping it more than, say, aluminum. What's going on? Okay. And and if you haven't seen this or done this, there's plenty of YouTube videos I'm sure you can find. I can show you this. Though it is pretty cool to see yourself in person. All right, so what is happening? Let's just think first before we start writing things down. I have a magnet, and so I can think of this magnet as a dipole, of course. Going down there. So then I have this thing. Let me draw some representative field lines of this dipole. Looks pretty good. It's going down, goes back up on these sides, and eventually goes back into the South Pole. So then what is happening then when we drop it through the pipe? Well, the copper pipe is a conductive material, so as the magnet goes through, the flux through various sections of the copper pipe is changing as the magnetic field moves through it. So in these regions of the copper pipe, let's approximate it instead not as a pipe. Let's essentially think of it as a bunch of very thin rings. I can draw this for the entire pipe, but I think you get the idea. So you can think of it as a bunch of thin rings, and each of those rings then form a well-defined closed loop. Each of those rings then experience a change in magnetic flux as the thing falls through, and within those rings, since copper is conductive, we get what's called an eddy current. A current that forms from this magnetic induction, named because if you take like a slab of copper and move a magnet over it, you get kind of vortices of current. So the eddy currents are named kind of because they look kind of like eddices and vortices in water, or in fluid dynamics, excuse me. So in this case then, as this magnet falls through, eddy currents are created. Those are just the induced currents. Those induced currents, of course, create a magnetic field to try to return things back to the good old days. That magnetic field then acts on the magnet that's falling through the pipe. Let's convince ourselves that the net overall result is that there is a force that opposes gravity. So what we're going to do is, rather than do this for an entire pipe, again, since we're just being qualitative, we're going to do this for, essentially two rings. A ring that's kind of right above the magnet and a ring that's right below the magnet. I don't have to copy everything. All right, that works. So let me copy this again. I'm so insistent that this looks perfect. I'm sure it's making great content. Okay, whatever. Good enough. So we have here, we're going to break it up into two rings. And then we're going to have the magnet at this moment be located right in between them. So for example, it might be that the magnet is here, and what we're doing is we are focusing on perhaps maybe like this ring, and then a kind of similar ring that's right below it. Because as the magnet falls through, eventually, when it's fully immersed, it will have part of the pipe that's above it and part of the pipe that's below it. So what we're going to do is analyze two rings, one above and one below. This kind of permanent dipole magnet. Okay, so let's start with the one on, well, we might be able to do both of them kind of simultaneously. Top and bottom. So let's look at what our surface is. So our surface, that we're measuring the flux through, is essentially the pipe. It's a conducting volume in a sense, because the pipe has some thickness. So we're just going to approximate it as a circle. So then we have a surface up here as well. Those are our surfaces that we're going to measure the flux through. We have to then define our dA element. We can choose a different one for each. We can choose the same one for each. I will choose, again, to make one of them always be positive, I'm going to choose the dA element. I made this too thick. I'm going to choose the dA element. That's going to go down for both. So, in that case, again, that's just defining what positive flux means, because we only care about change. So we just need a number. We need to just throw down a number line, which is what the dA element essentially is. So then on the top, what we're going to do is we're going to think of the magnet as it is in this picture, and then we're going to imagine, if the magnet fell, a centimeter more, how has it changed through those two particular surfaces? So the start here, right, start in picture, and then the end, not quite going to the calculus limit, but we're going to say, after the end point is going to be after the magnet falls. I don't know, right? 1 additional centimeter or something. So it's just a little bit lower, right? I just don't want to say that it's gone all the way through and now it's on the other side or something, right? It's just a little bit lower down. So then the start and end, we have to think about what is the flux and how has it changed? So for the start, through the bottom, there is positive flux going through. It looks like more magnetic field lines, because they're really concentrated right at the north pole of that magnet, are going to be going through that dA element in the direction of the dA element. So the flux is going to be positive. And then similarly up here, the flux is going to be negative. The flux is also positive in that case. Because again, they kind of loop up and then they go back down into the south pole element. And you might say, it looks like some of them are going up as well. You're exactly right. In this, where's the laser pointer? Where like for this field line, it looks like it goes up and goes up that way, but then it comes back down that way. And then this one, might do something similar as well. Then there's going to be some element here that goes something like this, that only goes down through that element. And there's going to be some field line over here that doesn't go up through it, but then does go down through it. So overall, there's going to be a net positive flux, because there are more field lines going down this way, which is closer to being parallel to the dA element. And maybe I'll even draw one of the, some of those, so it's even clearer. Okay, something like that, something like that. There is the net field is pointing closer to parallel to dA. So then what about the end? It's fallen a little more. So it's a little bit closer to the bottom element. So then I would say the flux is positive still, and that it's increased. It's more positive. And that in this case, the flux is going to still be positive, but it has decreased. It's getting farther away from the top element. The magnetic field is getting ultimately weaker there. So then the delta flux for the bottom, words were we using in the previous question? Decreases, negative, again, just whatever one makes most sense to you. So we would say that the flux increases in that it tended towards the right on the number line. There's more field in the direction of the D element, where here the magnetic flux has decreased. The overall magnitude of the flux is now farther to the left on this number line. So that is, the change. I'll draw the arrows in a second. So then the induced magnetic field, let me, again, sort of focusing again on these dA elements. So increases, so we'll say that dA is parallel to the dA element. And here it decreased, so then the flux, this little flux, we'll call it vector in quotes, is anti-parallel to the dA element. So then the magnetic field that's induced must then be the opposite. So this one is anti-parallel to the dA element. This one is parallel to the dA element. So let's come back up here. Starting to get a little busy. All right, I'm going to redraw it again. I'm not going to care so much about it being fancy looking. So we have the lower ring, the top ring, and the magnet. Remember, for this particular experiment, we put north on the bottom, south on the top. I'll let you work it out. If you flip it, does that change anything? So then for the bottom loop, we said that in this case the flux was increasing, so parallel to dA. Again, we had dA that way. I guess I was putting those on here so I can do that with our surface that we're measuring the flux through. It really is bugging me that the stock one is not the same size. I'll try not to redraw it. And then we said this dA element was pointing in the same direction. And we found that the flux decreased, so that it should point the change was anti-parallel. So, in that case, the induced magnetic field must therefore point for the bottom in the opposite direction, and in the top must point in the I flipped these, didn't I? Well, thankfully, I just flipped these categories. This was the bottom, this was the top. Let me just make sure. Increase, decrease. Okay, yes. Sorry about that. So then, in this case, if the flux decreased or was anti-parallel, then we can make this point in the direction of dA. So then, what does that mean? By right-hand rule, if this current goes this way, then by the right-hand rule, that will create a magnetic field that goes up through the loop. And then, in this case, up in the ring above, the current goes in the opposite direction. So by the right-hand rule, the current goes through the loop, through the top of the loop, out the bottom of the loop. Now, we have to ask ourselves, look at this. Why don't I just redraw the arrow? Why am I doing this? I don't know why I'm so picky today. So now in this case, we have to ask, we have those induced magnetic fields, and I'll draw a couple loops to help us out here. It comes out like that. And this one is coming out like that. And now we have to ask ourselves what forces are going to be felt by that permanent magnet. And here we have to just draw from our experiences of what we did in high school playing with magnets in terms of forces. Because again, the forces is because of moving charges, but it's because of these quantum mechanical things like electron spin and stuff like that. So what's going on? Remember that we draw field lines coming out of the north side and going into the south side. So for the bottom ring, you can think of that magnetic field as kind of a magnet that looks like that, because then that would create the same kind of dipole. And then on the top, you can think of it as something like, it's not big enough, as something like this, where there is a north on the bottom and a south on the top. And so what happens? Well, notice here we have kind of the north poles near each other, so that's going to feel a repulsive force. So the bottom ring is going to want to push the magnet up, which that works, right? Because we want something to resist gravity. And then the one on the top is going to want to be attractive, because you have a north pole and a south pole close to one another. So this seems like it should be attractive, which again is in the right direction. And so then notice at the end of the day, if you were to do a force analysis on the falling magnet, you have the force due to gravity, and then you have some force due to the magnetic field pulling up on it. That actual force, if you want to be quantitative about it, right, it's a change in flux, that's a time derivative, so the speed that the magnet is falling does affect the amount of current that is generated. These eddy currents that form around in the copper pipe. So that we would then expect that force to be velocity dependent, like a friction, and therefore there would be some terminal velocity where the force balances gravity, and then you have no net force, and then it just whatever speed it's at that point, that becomes its constant speed. Now, in this case, why does the magnet fall faster in a aluminum pipe? And as a hint, I will point out that aluminum is less conductive than copper. Well, this amounts to, let's break it down again. The magnet fell through the pipe. That created a change in flux through the rings of the pipe. That then created an induced, right, in order to create that magnetic field to bring back the good old days, that created an induced current. Really, what Faraday said is that there is an induced EMF in that ring. That EMF then drives a current such that it wants to cancel things out. However, right, I've always been saying it wants to get back to the good old days. If a current's going to flow, we know that current is resisted when there's a lot of resistance. We also know that if we have a coil, we wrote down the magnetic field for a coil. And it depended, of course, on the current, the amount of current that was going through that particular coil. You can just write it down real quick. All right, we wrote down, assuming I remember it, right, for a coil, where up is that way, so the current is kind of going in this direction. Or I'll draw out that as an arrow. And of course, the field is some sort of dipole. And we look particularly at the field along this kind of central symmetric axis. So B of the coil, along that kind of symmetry axis was something like mu naught times I, something like pi r squared or something like that, over 2 r squared plus c squared, so 3/2. If there's constants missing or something, forgive me, but this is the basic idea, right? We had an expression. We know what that magnetic field looks like. It depended on the current. So if the current is resisted or lower, the magnetic field that is therefore going to be weaker. That's the one that's created by this coil. So, right, if we think of the copper ring, the copper loop, right, we could think of it as once there is an induced EMF, that in that ring is a little magical battery that appears that has the induced EMF. And of course, there's some overall internal resistance. It's not superconductor. So in that case then, in the bottom loop, for example, when current flows in this direction, a good old Kirchhoff problem shows that the induced EMF minus I times the resistance of that ring must equal 0. And so therefore the current depends on the EMF that's created. That's, this is determined by, Faraday, or the change in flux. And then this is, right, I guess the resistance of the ring, right? It's a property of the circuit. So, if you have identical tubes, but one's copper, one's aluminum, the aluminum's not as good of a conductor. Think of it as having a much higher resistance. They both have the same change in flux. If there's two moments where the magnets are falling at the exact same speed, they would have the same change in flux in those two instances, but there would be a larger current created in the copper compared to the aluminum. That current would then create different strength magnetic fields that would then resist the motion of the magnet that's falling. That's the idea. So kind of cool. And these eddy currents, right, have a lot of cannot be ignored in a lot of electrical applications. All right. Let's see, now we're going to do some quantitative examples. Of course, by quantitative, I mean we'll have some symbols. I refuse to plug things in, do calculations for this sort of thing. I'll let you do that. Here's an art. Let's do this example. So you have a coil ring of radius r, and it is moving horizontally with a constant velocity to the right. And eventually, and we'll say at t equals 0, the ring begins to enter this region that has a uniform magnetic field. So it enters a region with a constant magnetic field, which looks like it's pointing out of the page. The region is length 4r. I would like to know, for this ring, is there ever current induced? If so, what direction? Or can I give intervals of time where there is a current and then give a direction? That's more the qualitative side of this. Then I would like to calculate what is the average induced EMF or the average current in this wire coil from the time where it's about to start entering the region to when it's fully immersed in the region. So let's do, we'll call part A. And then we can also, again, for some of this, we'll also assume the coil has internal resistance. Little r. So we could say part A, when is I induced non-zero? Well, I induced is a result of an electromagnetic force that's induced. Electromagnetic forces are induced when there's a flux that changes. So, in this case, when it's out here, of course, there's no flux and there's no change in the flux. It's just 0. Then at t equals 0, it hits this point. Then it starts to do this. Now suddenly there is flux going through this loop until eventually it gets here. During that phase, there is a change in the flux. During this phase, in that case, since the magnetic field is uniform, there's no change at all. And then on here, we are leaving the region, and we see that the flux goes away. So, when is the induced current non-zero? Since the induced EMF is given by a change in the magnetic flux, the magnitude is just the derivative. Of course, Faraday's law has that negative sign. Then we could define, say, delta t as just big R over V. What's that? Well, if distance is velocity times time for a constant velocity, then the time it takes to go the radius of the ring is just R over V. So then if we are to make some sort of qualitative plot, as a function of time, and here we're going to ask ourselves about, what is the magnitude of the induced current? Where we'll take the induced current to be positive or rather, on this plot, we'll plot it as a positive number when it's counterclockwise. We'll follow the usual convention like angles, and then we'll say that the induced current is negative when it's clockwise. That's just a convention I'm creating here on the spot, just for the sake of this problem. So we could first ask ourselves where it's non-zero. So maybe I could shade the region on this plot where it's non-zero. And let's break it up into like how much time, we could ask how much time does it take if it starts here at t equals 0, then this is delta t, this is t, this is, if this is 0, this is delta t, this is 2 delta t. Then it is 3 delta t, 4 delta t, 5 delta t, 6 delta t. So it looks like it takes 6 of these delta t's to get through. That makes sense, right? It's the region is essentially 2 diameters worth. So that takes 4, and then there's the kind of enter and exit. So let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 delta t's. Right here, I'll do it like this. I'll write that number as 6, and what this axis is plotting is t divided by delta t. So in that case, then, if 0 is when it's here, then there's a change in the first 2 delta t's, and it looks like there's a change in the last 2 delta t's. So maybe I'll shade that in on this plot. How about blue? No, yes, I won't do too much at once. Oops, we gotta go past 6. Yeah. Right, so the first 2 delta t's, and then the last 2 delta t's. We expect there to be something, and it's 0. Otherwise, it'll be 0 past this as well. All right. Now we have to actually try to figure out what this amount will be. All right. Now let's figure out the direction, because I guess we're still being qualitative. So, in the kind of as it enters, we'll break this up into the as it enters region. Well, we have to again define our dA element because we're measuring flux. So let's highlight and call. Here's the dA element that we're going to focus on. And again, to keep my life sane, since the field is always going to be pointing out of the page, let's let the dA element also point out of the page. So then, as it enters the region, more and more of that ring is immersed in the region where there's a magnetic field. More and more field lines are going to be entering as the ring enters. So right through the ring increases. And again, we could think of this because the part B is going to ask us to compute an average. So let's have the start and end be start will be t equals 0, and the end will be t equals 2 delta t. So when it's just about to start entering, but none of it is in the field, and then when it's finally that last snippet has gotten the entire ring into the field region. So in this case then, right before it starts to enter the field, there is no flux. And then when it is fully immersed in the field, it's a uniform field. The field is pointing the same direction as the dA element. I'll just write down the integral because we haven't yet for this lecture. Remember, the flux is defined as this. It's a constant field. The orientation is not changing. So this is the same thing as the magnitude of the field, the total area, that's shaded, and then some cosine factor of the angle between the field and the dA element. That angle is 0, cosine of 0 is 1. This looks like it's just the magnetic field strength times pi r squared, the area of that circle. Okay. The delta flux is, again, then it looks like it's just pi r squared b minus 0, or positive pi r squared times b. Notice in this case we can, since we might as well do part b along with us, that we can calculate an approximation or an average to how the flux has changed through these 2 points. And we can also evaluate, an approximation for the derivative. So it looks like then this would just be pi, well, sorry, let's be careful. Delta t is, right, delta t, what I mean by that is, let me write like this. The derivative of the flux is going to be approximated as this delta flux over 2 delta t. Because the way I've defined delta t, right, that's how long it takes to go from the start to the end fully immersed. So let's move over. So that, in this case, is going to then be, well, the numerator we just estimated, and then 2 delta t, and then we said delta t is r over v. One of the r's cancel, the v goes up top, so it looks like you get pi r v b all over 2. That's an approximation or an average value of the derivative of the flux change, also positive. So in this case then, since it is positive, I should have made this all, blue. Make it blue. I don't know why the one green fairy never made the dress green. I always wanted the dress to be green. Anyway, Sleeping Beauty reference. So in this case now, the change in flux, or the derivative of the magnetic flux, is positive, right? We'll call that increasing, right? It's increasing on the number line, which means, if I were to draw the blue arrow to represent the change, the kind of delta flux arrow is then going to point also out of the page. Again, parallel to dA. So then, as a result, the B induced then points in the opposite direction, so it will point into the page, or anti-parallel to dA. How can we have this happen? I'll redraw the loop. So as the flux is increasing, maybe I'll put it kind of partially immersed in the field here. As it's moving to the right, the flux is increasing. We then expect the induced current to go in the counterclockwise. Nope. Wrong right hand. Again, right hand rule. My thumb points, I want my fingers to, as I curl them through the ring, they go like this, or like this, to oppose that change in flux. So to do that, we have, or did I draw it right? No, I don't remember. Oh, good to spot check anyway. something like that. Because again, then that would oppose the field, the flux that's coming out. So in this case, then it looks like we expect then the induced current to then be where's my highlighter? To then be something. If we're going clockwise positive, or sorry, clockwise negative, counterclockwise positive, this region is going to be actually, right, something in the negative. We'll give it a little green tint. In this case. Now we can think about when is it going to be maximized. So the magnitude of the induced EMF, really this is the average value, is then going to be equal to this approximation we had for the derivative, which we wrote down was pi RVB over 2. Now that's the average value, so we could have some sort of average value here, right, that does something like this, then it drops to 0. So this would be pi RVB over 2. And again, I'm making it negative, I'm just saying clockwise negative, counterclockwise positive. But again, the axis is not right. You might say the unit's wrong. Because this is the induced EMF, and then for the circuit, then you have the induced EMF minus IR equals 0. So then the induced current looks like it's the induced EMF divided by the resistance, which we said was a little r, not big R, sorry. Something like that. So then I put a little r here in the bottom. Right, that's kind of the average value of the induced current. Now what actually happens, if we go back up to the full image, when is the derivative big and when is the derivative small? Well, if we take our circle again, when it's here, then as it's starting to enter the field, only a little, it's kind of the, there's not a large increase in the area that's now immersed in the area compared to when you're kind of here. And there's a big kind of change. If I move over a little bit, I have that whole big strip of new area. Versus here, I'm not introducing a lot of new area into the magnetic field region. So it seems that around here is when, if I move over, I have to put a big old vertical strip of new area in compared to here. So I would expect then, if we go back to this plot, that the actual current is going to look something, like this. Because the change in flux will be maximized kind of when it's half in, half out, and then on the edges, there's not as much change in flux. I'll let you work on your own. What the other side will be, perhaps unsurprisingly, it's by the symmetry of all this, there's a symmetry to the answer. BV over 2 a little more. It's kind of the average value again, and you would expect to kind of have that same similar shape as it leaves the field. Okay? Try another one. See, this one's the rails one. Maybe, okay, 54 minutes. Suppose I have two conducting rails. It has a resistor connected over here. Then I have a rod which is moving in this direction. It's also a conducting rail. And I would like to know, so we have some V, which this time we're going to make the function of time. So as you know, the rail moves, or I guess, I guess it's on rails and then it is a rail. I guess we'll call it something else. As the vertical rod moves along the rails, with, let's see, we'll make the gap, just kind of move this over. We're going to have this distance here be a length L. So with gap length L, this resistor has some resistance R. Rod moves along the rail with gap L at a speed given by, and I don't know, what are we feeling? Exponential? Sure. The velocity is given by some v naught e to the minus t over t naught, say, where v naught, t naught are constants. Essentially, it's exponential decay. All it means is that the speed is just exponentially decreasing over time. It's given by that velocity and is located at the resistor at t equals 0. Find the induced current, direction, and analytically solve for it as a function of time, and find I induced as a function of time. I guess I do have to do an integral, but exponential is so easy. So, okay. Very good. So, and then just to give a grid, let's call this location, we'll call that x equals 0, and this is then the positive x direction. Okay. A lot going on. Not that bad. So as the rod moves to the right, you might already see that this then forms our circuit. Or this is what I've just shaded is the area enclosed by our circuit, our complete circuit. Current will flow kind of clockwise or counterclockwise. Oh, I didn't even create a magnetic field. You would say nothing happens. There's no magnetic field. That's a trick question. So if I make that's kind of my region, and let's put the entire thing in a magnetic field so that this isn't a complete waste of time. So let's have the entire region in a magnetic field. So B is a constant in this region, and we can also point out the page. So we can say entire region is, or entire device in a uniform magnetic field. Okay, so now as the rod moves, that shaded region will have more, well, in this case, this example of, we asked ourselves in the last lecture, how can you change flux? And we essentially wrote down 3 things. You can change the strength of the magnetic field, make it stronger or weaker. That's been, I think, most of the examples so far. Well, actually, no, the previous example also was this case. So if we just use some of the previous examples, this eddy current stuff, how did the flux change? Well, we were changing the strength of the magnetic field through that surface. That was the kind of primary way to change the flux. How did you change the flux in this case? Well, we were changing the area that was immersed in the magnetic field. Right? More of this area became immersed in the magnetic field. I shaded this entire thing red. Really, it's kind of whatever part was immersed. And that's why we're doing an average in this case. If you wanted to do this analytically, you would have to solve as a function of time kind of how much area is within the magnetic field as a function of time. You could do that, use polar coordinates. But we didn't want to do that right now. Here, again, if the rod starts here at t equals 0, then it's here, then here, then here, then here. So then this is an example, again, where the area is changing as a way of changing the flux. And then I'll end with a problem where the orientation changes, where you have a field in an area and maybe the object with the area rotates or something. Okay, so in this case, then, let's define our dA element, which is all the way up there. Let me copy that picture, move down here. Something to draw on. Let's see, and I don't really need this box. It would be. So, in this case, what's happening? Well, we just look at this particular snapshot in time. The way we've defined is we said x0 is here, and then it has traveled out to a distance of x at this point in time. So x, which is itself a function of time. And then this length here we said was L. In the uniform magnetic field, then, the flux at this particular instant, which is B dot dA, the field is a constant, the orientation is not changing, so it's just B times the area times cosine, and again, I've defined it so it's the angle is 0, so this looks like it's B times A, but then that A, the area, is that length L times the value of x as a function of time. So to evaluate the total flux, I need to know x as a function of time. That's not too bad, because I know v as a function of time. So again, this is the area. So if v is a function of time, we said was some constant, either negative t or t naught. And I know that velocity, it's a 1d velocity, so I know that is the derivative of a position. I can then write that dx equals v naught e to the negative t over t naught dt. I've effectively separated variables in this hella simple differential equation. Give a little more space in here. Now I can integrate both sides. And at t equals 0, we said that x was equal to 0. Because again, remember, back to whatever lecture this was, this is an integral over time, because that's what's here. So if I want to have limits, these limits have to be time values, just as in these limits have to be x values. The fact that these are both 0 just happens to be because I said x equals 0 when t equals 0. If that's not the case, these might not match. And that's okay, because this is a position, this is a time. And then I'm going out to some later time t, in which case then the position is then, we're just going to x of t. Again, I like doing definite integrals. I don't like dealing with constants of integration. So I have my kind of, in a sense, I'm looking for the variable x, and I have it as one of my limits. So that's a pretty easy integral on the left to do. So let me just copy this. So then the left integral just becomes x of t minus 0. Then the right hand side when I do the integral, that becomes v naught e to the minus t over t naught divided by negative 1 over t naught. Again, how could you check? Well, the integral is the antiderivative, so I could take the derivative of this expression, and I better get back v naught e to the negative t over t naught. And by the chain rule, right? The derivative of the exponential is itself, then you have to pop out the derivative of the thing inside the exponential, which would be negative 1 over t naught. And then this is evaluated from 0 to t. So, let's see, what do we get? So, well, maybe I'll algebraically simplify first, since I know some of this is still kind of new to people. So if I algebraically simplify first, I get that. There's that negative, so I could just plug things in and take the negative along for the ride. But I also know that a negative can be used to swap the limits. So I could do something instead of from 0 to t, I'll go from t to 0. Which then, why is this so zoomed in? And now let's plug in. And then the constants v naught and t just go along for the ride. I plug in 0, e to the 0 is 1. Then I subtract what I get when I plug in t. That seems to be my expression. Does it dimensionally make sense? Yes. The stuff in the exponential is dimensionless because it's t over t naught. 1 is just a number, and then v times t does indeed have units of distance. All right, so then it looks like at the end of the day, I've written down that x as a function of time is v naught times t naught, 1 minus e to the negative t over t naught. And then notice if I plug in 0, I get 1 minus 1, x equals 0. So then, it seems like we have flux equals b times a, which we now can write down as b times L times v naught times t naught times 1 minus e to the negative t over t naught. Whew. So, if I think about that, what does that look like as a plot? A plot of this, again, it's when I plug in t equals 0, I get 0. And when I plug in infinity for t, I get BL v naught t naught. So it looks like it is an exponential that asymptotes to BL v naught t naught. Again, I'm coming so full circle with these lectures. All right, does that have units of flux? Flux is field times an area. I have field, and then I have a distance, and then we have a distance. Okay, so that's the flux. The nice thing is that if you have it analytically, you might think this was kind of harder, but if you have it analytically, you don't have to think about start and ends, because we have the time derivative. Now we can just take the derivative of this thing. B, L, V naught, T naught. Then I have to take the derivative of that thing in parentheses. So the 1 goes away. Then I have negative. The derivative of the exponential is itself. And then chain rule, 1 over T naught pops out. Seems like some things cancel. These negatives cancel, these T naughts cancel. So then it looks like this becomes looks like B, L, V naught. Yep, and then that's it. And times e to the negative t over t. So the time derivative of flux looks like instead it is a decay. Something like this. And it's always positive. And that makes sense because just given the value of the flux. The flux always seems to be increasing if you look at the top plot. So then its derivative must always be positive. and asymptotes. Okay, so everything's kind of scattered now over parts of the page. So once again, make a copy of this thing. So there's our circuit. I would say you can still, and it's probably good to do, we can still qualitatively, try to predict the direction of the current. That's usually what I do anyway, and then I use the math to give me the exact values. So the flux is always increasing, right? That's what the plot at the above is showing. The flux is always increasing as defined by our direction for dA, which I never said. Man, I'm getting tired. I really never said dA? Wow. Boy. All right. So we had to choose a dA element, else my flux integral, there's that cosine factor. So again, we'll have dA also point out of the page. Again, dA pointing out of the page. Yeah, I needed that, or I made that implicit assumption here. All right, when I said the angle between these two things was 0, that cosine is just 1, I was making this assumption without saying so. Whoops. So the flux is always increasing. So again, if we want to use our color conventions I've been using, so that implies that since this is what we've been calling the thing in blue is positive, right? Or you can think of it as it's increasing. So this arrow points parallel to dA. So then the induced magnetic field must then point in the opposite direction. So it must point into the page, anti-parallel to dA. So by the right-hand rule, which direction can you draw the current and have the induced magnetic field point into the page? You can only do that if it goes in a clockwise direction. And so that is the direction of the induced current. And a right-hand rule, as it goes around, it always is going through that red region into the page. Now, the induced EMF, which in magnitude is just the time derivative of the flux, we have worked out to be BL V naught e to the minus T over T naught. And again, the simple circuit looks like it's induced EMF minus I times R equals 0, so that the induced current is, in this case, equal to. Make sure I'm not calling two different things R. We have that out front, and then an e to the negative t over t naught. It exponentially decays. That kind of makes sense. As the rod is moving, it's kind of, new strips of area are being brought in, and the size of the strips aren't changing like it was for that circle, but the speed at which we are adding new strips is slowing down because the rod is slowing down. I guess if we want to highlight the answer, that would be the answer. Okay. Time. What quantitative do I want to be about this one? Yeah, well, whatever, let's do it. All right, last example. So let's have a 3D system. I'm sure as soon as I said that, people logged off. Here's the z direction, x, y. let's have B point B is uniform and along the z-axis, so that I can actually write B as a vector. I'll use a column vector notation of x is 0, y is 0, and it's some constant in the z direction. Right, that describes, as a vector, the magnetic field strength and direction. Or if you want to use engineering notation, of course, that's just k, or sometimes x, y, z are used with a little unit vector. Okay, and then let us have a setup that kind of looks like this. So it's got two spokes. That's supposed to be a circle. I should just, let's see, can I? So in this circle, I have a circular coil. It's not a circle. Still not a circle. Let's draw a circle. There we go. I have a circular coil that has some insulating rods that it's attached to, and they're supported on these spokes, such that it could rotate if I wanted it to. It has some radius r. It is a coil that has some small internal resistance. And let's say that through some little motor, we do get it rotating. It starts rotating in that direction. So it's kind of rotating like that. And this coil rotates once every 4 seconds. So it's rotating, and the entire device is placed within the magnetic field. Find the induced current as a function of time. Okay. In this case now, this is an example of how do you change flux. You could also change the orientation, because now our area that's enclosed by our circuit is this here. And if I define dA to say be like this, and I guess to orient it on the axes, we're going to have the device is along the x-axis. Sorry, let's do the y-axis. So it kind of matches what I've drawn. Yeah. And such that at t equals 0, that little dA element I just drew points along the x-axis, the positive x-axis. So this entire thing is kind of along the y-axis, then dA is pointing along the x-axis. So does that drawing work? Yeah, that's better. And then the magnetic field is pointing uniform everywhere along the z-axis. So in this case, as the circle rotates, sometimes it's, the dA element is going to be perpendicular to the magnetic field, like how it's kind of drawn in the picture. No field lines are going through the circle at that particular moment. But then when the circle is rotated so that it's flat, or in the xy plane, then it has maximized the amount of flux, at least in magnitude. We'll worry about direction in a little bit. And then it kind of goes between lots of flux, zero flux, lots of flux, zero flux, lots of flux. So what's going on? Here again, I'm creating a dA element that I now have to be consistent with. And I'm going to use that to define this rotation. If I say it rotates once every 4 seconds, I can also think of it of that dA vector has to complete one full circle in the xz plane once every 4 seconds. So that's nice because that gives me a pretty easy way to write down dA. Which I will again write as a column vector. If it's in the xz plane, then the y component is 0. At t equals 0, it starts along the x-axis, which means the z component is going to be the sine. And by the way, it's rotating. Looks like this should be negative sine omega t, and then this is cosine of omega t. And this is well, I guess this is the unit vector version, right? Because if you take the magnitude of that, it has unit magnitude. So dA unit vector version is that. Because omega then tells you the angular frequency that it rotates at, where the angular frequency, which is related to the period by 2 pi divided by p, so this is going to be 2 pi divided by 4 seconds, or it's going to be pi over 2 radians per second. That's the value for omega. And then the total area of the circle is of course pi r squared, so then I can write dA, the vector, where its magnitude is pi r squared, and then its directionality, its directionality is given by the unit vector, cosine, let's see, pi t over 2, 0, negative sine, pi t over 2. All right, that's nice. That's our dA. And again, plot that. You'll notice it just spins in a circle in the xz plane. And it's why negative sign? Because if you think of the way the drawing is, the dA arrow should start to point down once t starts to march forward and then loop back around. Okay. In many ways, this is the hard part, because once we have these, we have an integral formulation for the flux. It actually is not too bad in this case. I guess I'm calling this dA because we've been using dA a lot, right? The magnitude, right? Usually we said the magnitude of the dA element is then just little dA that you then integrated. Maybe I should call this kind of the A element. So that implies this is the A element. Such that if I want to then evaluate the flux, which is the integral of B dot dA, but B is uniform, but the orientation is changing in this case. Yeah, so let's see, if this is, let's call it, we said this was the unit vector version. Let's upgrade this and give it a magnitude of dA, and then we'll call this the dA element. So in this case, looks like then this is the integral of the dot product. I'll write this with kind of as a row vector. So we said B was 0, 0, B naught. We are dotting it with a vector that has cosine pi t over 2 dA, comma 0, comma negative sine pi t over 2 times dA. And this is all, that's it. Because the dAs are kind of in that vector now. What a mess. But the dot product saves us because I can just do the x's, the y's, the z's, add them together. Looks like then I get negative b naught sine of pi t over 2 times dA. This is an integral over area. So in this case then, what do we get? we just get that, right, this is an interval over area, not time. So at the end of the day, we're going to write it's just negative b naught pi r squared sine of pi t over 2. I feel like I'm missing a variable. Nope, okay. Because we're integrating over the area. So in this case, this is a measure of the flux. So let's make a plot of this and see if we can understand what it looks like. There's going to be ultimately 3 plots I want, so make sure I leave enough room. Yeah, I want negatives too. So let's do this. It's time. Copy that 3 times, or 2 more times. Maybe 1 extra for good measure. Oops, not need to cut. So, let's see, this first one we're going to plot is the flux. And the period is 4 seconds, so let's go up to 6 seconds. So 1, 2, 3, 4, 5, 6. So then this just looks like it's negative sine, so sine starts at 0, but there's that negative there. So 1, 2, 3, 4, and 5, 6. So it looks like that's the a measure of the flux, and it's reaches an amplitude of b naught pi r squared. Negative there, positive up top. Okay, so the total flux through the loop is changing. Again, there's no flux through the loop initially, then it kind of increases, but in the negative direction. Why negative? Why does it start negative? Well, let's think about at t equals 1 second. The loop is now horizontal, right? Horizontal in that. That's the x direction. That's the y direction. And then the field in the z direction. Remember, the field is pointing this way. And then our dA element we said is going to be pointing down at that point. So negative flux at first, then as it rotates halfway around, then dA and B are in the same direction, and then repeats. So now we have to ask ourselves, is a change in the flux? Well, derivative of sine, that's easy. Sine becomes cosine, pi over 2 pops out, so I have b naught pi squared r squared all over 2 cosine of pi t over 2. Chain rule, chain rule, chain rule. So the change in the flux, we'll have a plot for the derivative. Change in the flux. I want the tick marks to be matched. Okay. So it looks like starts negative with a cosine. So cosine starts down here, then 1, 2, 3, 4, 5, 6. All right. And then again, this is negative b naught pi squared r squared over 2. So that gives us a sense of the change in the flux. Now here, the fact that it goes from negative to positive, we can take some meaning from that, because that means how the flux is changing, right? It's getting, because think back to the number line. We only care about whether it's increasing, which means it's in the positive direction, and then it's decreasing towards the negative direction. So in this case, let me write that better. And then you just have to be very careful about kind of what you're looking at, what you're plotting. So we would say that the flux, when it's greater than 0, that corresponds to increasing. Or that our kind of blue arrow, or we said that, and that means our blue arrow is parallel. We had a little double line that is parallel to dA. And then when the flux derivative is negative, that corresponds to decreasing, or that our blue arrow is anti-parallel to dA. So let's use some highlighting colors to do this. Red has already been claimed. So when it's parallel to dA, let's use blue for that. And when it's anti-parallel, let's use green. So if I look at the derivative, right, where that's plotting the value, so again, I'm only looking at the value. I'm not looking at the slope or whether it's positive. I'm just looking at whether it's positive or negative. So then it looks like this, the value is positive. Here, the value is positive. And then that means here the value is negative, and here the value is negative. And I want to then translate those colors up here, because it is that change that is going to help us see what's going on. Maybe I'll draw little pictures up top of what's going on here. So here, kind of, that's the start. Here's where it's kind of flattened. And then here is kind of when it's back to being like this. Here's where it's flattened. Let's see, it's back to being like this. That starts over. Then it's flattened again. So again, what I mean by that is a little dA element. So dA element is going that way, going down, going that way, going up. That's back to where it started. Again, with the field line always going up, 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 as it spins around. So then the induced magnetic field is the opposite in that case. Right, is the opposite. So then that just means, and the induced EMF is then just, we could think of it now, right, as if we wrote it as negative, the derivative, we could write this as positive B naught pi squared r squared over 2 times cosine of pi t over 2. Right? Really, again, the negative sign just means that it's going to be flipped. So you need the tick marks. Let's see the tick marks. Okay. So then I can have, it's the same thing with flips. So 1, 2, 4, 6. It's not perfectly straight, but that's fine. So the induced EMF, in this case, I'm going to copy the colors again, but I'm going to have the colors be what it was for the change in flux. Right? What was driving this was a change in the flux through the loop. So in this case, we have something that looks like that. And I don't think we actually need this. So in this case, it's an alternating current. because as the induced EMF changes sign, that also means the current is changing direction. So in this case, the current is kind of swapping sinusoidally back and forth. This is an alternating current. So yeah, if that coil has a little bit of resistance, then this is just pi squared r squared over 2 little r for the resistance, cosine pi t over 2. Where we think, how does it start? So it seems like it starts positive. It's the same sign as the induced EMF. So based on the numbers on your axes, right, this could also be I induced. And then given this, we then can think about whether a positive means, what direction corresponds to a positive current, what direction corresponds to a negative current. So let's see, let's take kind of one, let's see. Well, you can think about this kind of early part here. So what's going on in this kind of early point in time, in the first second. So in the first second, you're starting with no flux. Let's just look at the average. So at t equals 0, you have the loop and then dA is pointing like that. But then the magnetic field is perpendicular. Then at t equals 1 second, the loop has rotated, so that's kind of flat, where dA is pointing down, and the field pointing up. And again, just to highlight our areas, right, when we're looking at the flux through this. So again, we have the mathematical formulas, already on the screen or somewhere on the page. But again, this on average, this was the case where the flux started being 0 and the flux ended being less than 0. So that seems like that the delta was a decrease. Which means, like we said, that the green corresponds to our blue arrow is anti-parallel to the dA element during this phase. So then the induced magnetic field then is parallel to dA during this phase. And how can you get, let's see, how can I draw it? I'll draw the perspective. That's kind of flat. So you have this loop. And my dA element, this is, I guess, kind of right near t equals 1 second. And we've said that the induced magnetic field must be parallel. How can I get, by the right-hand rule, my fingers to go into the loop? It looks like the induced current is going in that direction during this phase. So in the regions where it's been highlighted green, I'm going to help make that point, right? So then this is the I induced for the green color. And then the blue then is the opposite direction, because then the flux becomes positive and it's getting more and more positive. So then the delta phi would be increasing. So the current kind of does something like this. It oscillates. In that case, see there, I think it's really clear of why really thinking about the dA element matters. Because in this case, we were able to think of just increasing and decreasing relative to this dA element, which really is just kind of putting everything on a number line where there's only 2 directions you can choose from. So what it means to increase or decrease is then only explained in terms of parallel or anti-parallel.
So once I have a change,
all right,
I'm going to draw it like I'm going to treat it like a vector.
Come to grasp with this admittedly very challenging topic.
This kind of, I've been using blue, this kind of delta flux as a vector, where again it's going to follow the rules in the previous line, where this change is parallel to dA, right, if positive, and it's going to be this anti-parallel to dA if negative. So in this case, the flux is increasing. So here, the change in flux is positive because the overall flux is increasing. It was positive to begin with, and it's even more positive at the end. So then I'm going to draw this arrow with the idea that it's kind of situated in the direction of dA. Then Lenz's law, or then Lenz says that the induced magnetic field must point in the opposite direction. So we've been using green. So I'm just going to draw this green arrow in the opposite direction. So in this case, since the blue was parallel to dA, this kind of green is anti-parallel to dA. And then I'm going to find the current that will allow me to then counteract this field. So let me copy this last picture, just so that we can have some sort of visualization. So in this case, all right, if I again use light blue to be the start, then the end, now the contrast is not quite as grand. The contrast is kind of that there's more magnetic field lines coming through the loop. dA is pointing that way. The flux is increasing, which means that the change, delta phi, is in that direction as well. The induced magnetic field wants to counteract that. Flux is increasing, meaning there's more flux down to the left. The induced B field, oh sorry, we said green. The induced B field, resize, must therefore point in that direction. And how do you accomplish that? Again, by the right-hand rule. Seems that if the current, hard to see, the current is going in this direction, that direction, I'm going behind all these things, that direction, that is the induced current, or also the kind of direction of the EMF. So you might also say kind of psi, comma, I. In that direction, by the right-hand rule, the induced magnetic field will try to counteract this change. And again, why does that work? Now we have too many field lines. So let's see, if I have a current that's kind of going like this, where is this being drawn? Okay. then again, the magnetic field by the right-hand rule, my thumb points in the direction of this arrow, and then the magnetic field looks like it's kind of going out and then in. It's kind of way too busy for you to see what's going on. So allow me to redraw it. So we have a loop, and then we're going to just only draw this induced current, which is in that direction, with the idea that the magnetic field that it creates by the right-hand rule kind of goes out and up and then down. That's not really the way to think about it, because the way it's oriented. Kind of goes out and around and then in and then out and around. Again, following the right-hand rule. Again, this kind of goes out, in, and it loops around in this direction. Not sure if that helps. Is again with the idea being that we want the induced magnetic field to ultimately point and match this arrow. Okay. So now we can try to do some other examples. What about the example where here we brought the magnet closer. What if we pull the magnet away? Should we have? Let me move everything that we don't need for that problem. There. And here we go with the next example. So, example where you pull the magnet away. And so the setup is going to be something like, here's the start, and then here is the finish. So let's call this start and call this finish. And I've already done a couple of the steps for us. Since I now have the way that the magnet's oriented is that the north is on the top and the south is on the bottom, notice that that creates field lines that kind of loop around. It comes out of the north and kind of loops around and might go into the surface this way, such that when I pull the magnet farther away, more of those loops are going to be completely contained behind this coil rather than going through it. There still might be, right, this one that kind of goes way out here might still go through in this general direction. So as a result, notice I made DA point in the opposite direction. So I could say for the first step, given the B field line directions, we're going to define the DA element. So the overall flux at the start is very much a positive number. So I'm dealing with positive numbers again. This required me to define the surface, which required me to define the circuit. I think we're kind of all set on all of that. So then I should have copied these directions to the other page. Right, we have DA, now we want to measure a change and then label that change in some meaningful way. So given B, the magnetic field, I'm going to define DA to be that way. So then at the end point, fewer field lines. Through the surface. they still would be going probably in the right direction, in that if I were to draw more magnetic field lines, right, the next kind of one that goes out might kind of do something like this. So it seems like they should still be going in the right direction through the surface. So I still expect the magnetic flux at the end, at the finish, to be positive. But if I think of the flux start plus this delta flux to equal the flux that's finished, it seems like the flux is overall decreasing. Again, positive is in the same direction as dA. I could even draw the kind of net flux, if you will. There's lots of arrows going through the surface, so maybe that's kind of the vector-ish interpretation of the original or the starting flux. Then at the end, there's fewer field lines going through, so maybe that's kind of a representation of the net flux. So if I just think of how I add vectors together, what vector do I have to add to that first vector to get the small little vector? Well, I have to cancel some of it out, so I might have a flux or a delta flux. It might look something like that. And then when I add this plus this, I get that. If I think of them as vectors. So let's see, I might even make a copy of this so I can move it down here to the text. And the delta is in that direction. So then what does that mean? That means then that the kind of magnetic field that's induced should point in the opposite direction. So this, it seems like the blue was anti-parallel to dA, because the flux is decreasing in that it's going away from the positive direction. The being induced should point in the opposite direction, so that arrow should point, be the flip. So this is then parallel to dA. That's all well and good. And then we just have to think about what direction the current has to be to do that. And it seems like then we have more or less the same as before. So in order to get the induced magnetic field, I should have made that green because we're sticking with green for induced magnetic field. If I go back up to the picture, it's not too busy yet. Essentially, I start with lots of flux going through the tube, and then there's not as much flux going through the tube. So wanting the good old days, it's going to create a current that's going to try to restore the flux to its glory days. So it's going to want to induce a magnetic field that points in that direction. You can get that if you have a current that goes in this kind of clockwise direction. Because then the field lines loop around, something like that. And by the right-hand rule, it kind of loops out on the outside and then in on the inside. And that goes to reinforce and restore the field.